soil liquefaction describes a phenomenon whereby a saturated or partially saturated soil substantially loses strength and stiffness in response to an applied stress, usually earthquake shaking or other sudden change in stress condition, causing it to behave like a liquid. In soil mechanics, the term liquefied was first used by Hazen in reference to the 1918 failure of the Calaveras Dam in California. He described the mechanism of flow liquefaction of the embankment dam as follows. If the pressure of the water in the pores is great enough to carry all the load, it will have the effect of holding the particles apart and of producing a condition that is practically equivalent to that of quicksand. The initial movement of some part of the material might result in accumulating pressure, first on one point, and then on another, successively, as the early points of concentration were liquefied. The phenomenon is most often observed in saturated, loose, sandy soils. This is because a loose sand has a tendency to compress when a load is applied. Dense sands by contrast tend to expand in volume or dilate. If the soil is saturated by water, a condition that often exists when the soil is below the groundwater table or sea level, then water fills the gaps between soil grains. In response to the soil compressing, this water increases in pressure and attempts to flow out from the soil to zones of low pressure. However, if the loading is rapidly applied and large enough, or is repeated many times such that it does not flow out in time before the next cycle of load is applied, the water pressures may build to an extent where they exceed the contact stresses between the grains of soil that keep them in contact with each other. These contacts between grains are the means by which the weight from buildings and overlying soil layers are transferred from the ground surface to layers of soil or rock at greater depths. This loss of soil structure causes it to lose all of its strength and it may be observed to flow like a liquid. Although the effects of liquefaction have been long understood, it was more thoroughly brought to the attention of engineers after the 1964 Niagara earthquake and 1964 Alaska earthquake. It was also a major factor in the destruction in San Francisco's Marina District during the 1989 Loma Prieta earthquake, and in Port of Kobe during the 1995 Great Hanshin earthquake. More recently, liquefaction was largely responsible for extensive damage to residential properties in the eastern suburbs and satellite townships of Christchurch, New Zealand during the 2010 Canterbury earthquake and more extensively again following the Christchurch earthquakes that followed in early and mid-2011. The building codes in many developed countries require engineers to consider the effects of soil liquefaction in the design of new buildings and infrastructure such as bridges, embankment dams and retaining structures. Technical definitions: a state of soil liquefaction occurs when the effective stress of soil is reduced to essentially zero, which corresponds to a complete loss of shear strength. This may be initiated by either monotonic loading or cyclic loading. In both cases, a soil in a saturated loose state, and one which may generate significant pore water pressure on a change in load are the most likely to liquefy. This is because a loose soil has the tendency to compress when sheared, generating large excess pore water pressure as load is transferred from the soil skeleton to adjacent pore water during undrained loading. As pore water pressure rises, a progressive loss of strength of the soil occurs as effective stress is reduced. It is more likely to occur in sandy or non-plastic silty soils, but may in rare cases occur in gravels and clays. A flow failure may initiate if the strength of the soil is reduced below the stresses required to maintain equilibrium of a slope or footing of a building, for instance. This can occur due to monotonic loading or cyclic loading, and can be sudden and catastrophic. A historical example is the Oberon Disaster. Casagrande referred to this type of phenomena as flow liquefaction, although a state of zero effective stress is not required for this to occur. The term cyclic liquefaction refers to the occurrence of a state of soil when large shear strains have accumulated in response to cyclic loading. A typical reference strain for the approximate occurrence of zero effective stress is 5% double amplitude shear strain. This is a soil test-based definition, usually performed via cyclic triaxial, cyclic direct simple shear, or cyclic torsional shear type apparatus. These tests are performed to determine a soil's resistance to liquefaction by observing the number of cycles of loading at a particular shear stress amplitude before it fails. Failure here is defined by the aforementioned shear strain criteria. The term cyclic mobility refers to the mechanism of progressive reduction of effective stress due to cyclic loading. This may occur in all soil types including dense soils. However, on reaching a state of zero effective stress, such soils immediately dilate and regain strength. Thus shear strains are significantly less than a true state of soil liquefaction, whereby a loose soil exhibits flow-type phenomena. Occurrence: liquefaction is more likely to occur in loose to moderately saturated granular soils with poor drainage, such as silty sands or sands and gravels capped or containing seams of impermeable sediments. During wave loading, usually cyclic and drained loading, for example seismic loading, loose sands tend to decrease in volume, which produces an increase in their pore water pressures and consequently a decrease in shear strength, that is, reduction in effective stress. Deposits most susceptible to liquefaction are young sands and silts of similar grain size, in beds at least meters thick, and saturated with water. Such deposits are often found along stream beds, beaches, dunes, and areas where wind-blown silt and sand have accumulated. Some examples of soil liquefaction include quicksand, quick clay, turbidity currents, and earthquake-induced liquefaction. Depending on the initial void ratio, the soil material can respond to loading either strain softening or strain hardening. Strain softened soils, for example loose sands, can be triggered to collapse either monotonically or cyclically, if the static shear stress is greater than the ultimate or steady-state shear strength of the soil. In this case flow liquefaction occurs, where the soil deforms at a low constant residual shear stress. If the soil strain hardens, for example moderately dense to dense sand, flow liquefaction will generally not occur. However, cyclic softening can occur due to cyclic and drained loading, for example earthquake loading. Deformation during cyclic loading will depend on the density of the soil, the magnitude and duration of the cyclic loading, and amount of shear stress reversal. If stress reversal occurs, the effective shear stress could reach zero, then cyclic liquefaction can take place. If stress reversal does not occur, zero effective stress is not possible to occur, then cyclic mobility takes place. The resistance of the cohesionless soil to liquefaction will depend on the density of the soil, confining stresses, soil structure, the magnitude and duration of the cyclic loading, and the extent to which shear stress reversal occurs. Earthquake liquefaction. The pressures generated during large earthquakes with many cycles of shaking can cause the liquefied sand and excess water to force its way to the ground surface from several meters below the ground. This is often observed as sand boils, also called sand blows, or sand volcanoes at the ground surface. The phenomenon may incorporate both flow of already liquefied sand from a layer below ground, and a quicksand effect whereby upward flow of water initiates liquefaction in overlying non-liquefied sandy deposits due to buoyancy. The other common observation is land instability, cracking and movement of the ground downslope or towards unsupported margins of rivers, streams, or the coast. The failure of ground in this manner is called lateral spreading, and may occur on very shallow slopes of angles of only 1 or 2 degrees from the horizontal. One positive aspect of soil liquefaction is the tendency for the effects of earthquake shaking to be significantly damped for the remainder of the earthquake. This is because liquids do not support a shear stress, and so once the soil liquefies due to shaking, subsequent earthquake shaking is not transferred to buildings at the ground surface. Studies of liquefaction features left by prehistoric earthquakes, called paleoliquefaction or paleoseismology, can reveal a great deal of information about earthquakes that occurred before records were kept or accurate measurements could be taken. Soil liquefaction induced by earthquake shaking is also a major contributor to urban seismic risk. Effects. The effects of soil liquefaction on the built environment can be extremely damaging. Buildings whose foundations bear directly on sand which liquefies will experience a sudden loss of support, which will result in drastic and irregular settlement of the building, causing structural damage, including cracking of foundations and damage to the building structure itself, or may leave the structure unserviceable afterwards, even without structural damage. Where a thin crust of non-liquefied soil exists between building foundation and liquefied soil, a punching shear type foundation failure may occur. The irregular settlement of ground may also break underground utility lines. The upward pressure applied by the movement of liquefied soil through the crust layer can crack weak foundation slabs and enter buildings through service ducts, and may allow water to damage the building contents and electrical services. Bridges and large buildings constructed on pile foundations may lose support from the adjacent soil and buckle, or come to rest at a tilt after shaking. Sloping ground and ground next to rivers and lakes may slide on a liquefied soil layer, opening large cracks or fissures in the ground, and can cause significant damage to buildings, bridges, roads and services such as water, natural gas, sewerage, power and telecommunications installed in the affected ground. Buried tanks and manholes may float in the liquefied soil due to buoyancy. Earth embankments such as flood levees and earth dams may lose stability or collapse if the material comprising the embankment or its foundation liquefies. Mitigation methods. Methods to mitigate the effects of soil liquefaction have been devised by earthquake engineers and include various soil compaction techniques such as vibrocompaction, dynamic compaction, and vibro stone columns. These methods result in the densification of soil and enable buildings to withstand soil liquefaction. Existing buildings can be mitigated by injecting grout into the soil to stabilize the layer of soil that is subject to liquefaction. Quicksand. Quicksand forms when water saturates an area of loose sand and the ordinary sand is agitated. When the water trapped in the batch of sand cannot escape, it creates liquefied soil that can no longer support weight. Quicksand can be formed by standing or flowing underground water, or by earthquakes. In the case of flowing underground water, the force of the water flow opposes the force of gravity, causing the granules of sand to be more buoyant. In the case of earthquakes, the shaking force can increase the pressure of shallow groundwater, liquefying sand and silt deposits. In both cases, the liquefied surface loses strength, causing buildings or other objects on that surface to sink or fall over. The saturated sediment may appear quite solid until a change in pressure or shock initiates the liquefaction, causing the sand to form a suspension with each grain surrounded by a thin film of water. This cushioning gives quicksand, and other liquefied sediments, a spongy, fluid-like texture. Objects in the liquefied sand sink to the level at which the weight of the object is equal to the weight of the displaced sand-water mix and the object floats due to its buoyancy. Quick clay. Quick clay, also known as leader clay in Canada, is a water-saturated gel, which in its solid form resemble a unique form of highly sensitive clay. This clay has a tendency to change from a relatively stiff condition to a liquid mass when it is disturbed. This gradual change in appearance from solid to liquid is a process known as spontaneous liquefaction. The clay retains a solid structure despite the high water content, because surface tension holds water-coated flakes of clay together in a delicate structure. When the structure is broken by a shock or sufficient shear, it turns to a fluid state. Quick clay is only found in the northern countries such as Russia, Canada, Alaska in the US, Norway, Sweden, and Finland, which were glaciated during the Pleistocene epoch. Quick clay has been the underlying cause of many deadly landslides. In Canada alone, it has been associated with more than 250 mapped landslides. Some of these are ancient, and may have been triggered by earthquakes. Turbidity currents. Submarine landslides are turbidity currents and consist of water-saturated sediments flowing downslope. An example occurred during the 1929 Grand Banks earthquake that struck the continental slope off the coast of Newfoundland. Minutes later, transatlantic telephone cables began breaking sequentially, farther and farther downslope, away from the epicenter. 12 cables were snapped in a total of 28 places. Exact times and locations were recorded for each break. Investigators suggested that a 60-mile-per-hour submarine landslide or turbidity current of water-saturated sediments swept 400 miles down the continental slope from the earthquake unregistered trademark S epicenter, snapping the cables as it passed. Research. The George E. Brown, Jr. Network for Earthquake Engineering Simulation hosts 2 geotechnical centrifuges for studying soil behavior. The NEES centrifuge at University of California, Davis has radius of 9.1 m, maximum payload mass of 4,500 kg, and available bucket area of 4.0 m2. The centrifuge is capable of producing 75 Gs of centrifugal acceleration at its effective radius of 8.5 m. The centrifuge capacity in terms of the maximum acceleration multiplied by the maximum payload is 53 G x 4,500 kg equals 240 G tons. The NEES centrifuge at the Center for Earthquake Engineering Simulation at Rensselaer Polytechnic Institute has a nominal radius, 2.7 m, which is the distance between the center of payload and the centrifuge axis. The space available for the payload is a depth of 1,000 m, width of 1,000 m, height of 800 m, and a maximum height of 1,200 m. The performance envelope is 160 G, 1.5 tons, and 150 G tons. See also, Paleoseismology, dry quicksand, Atterberg limits, mud volcano, sand volcano or sand blow, thixotropy, earthquake engineering, events attributed to liquefaction, Oberon Disaster, references. Further reading, Seed al. Recent Advances in Soil Liquefaction Engineering, a Unified and Consistent Framework, 26th Annual ASCE Los Angeles Geotechnical Spring Seminar, Long Beach, California, April 30, 2003, Earthquake Engineering Research Center PDF, external links, media related to soil liquefaction at Wikimedia Commons, soil liquefaction, shaking, liquefaction on Harbor Island, one of the few known live observations of an earthquake liquefaction event by a seismologist, video showing liquefaction process.